Welcome to the Forest Analytics Landing Podcast. I'm your host, Matt Russell. In this podcast, we'll talk about how data and analytics are transforming the forest products industry. We'll share how a research-based approach to analytics can empower your forestry organization to make better decisions with your data. Hello, everyone. Welcome to today's podcast. Today, I want to talk about random forests. Random forests have really exploded in their popularity in forestry in the last several years. And they are a quantitative tool, and many consider them a part of machine learning. And so random forests can be considered a machine learning technique. And so I'll present kind of two sections to the podcast. The first will kind of just give an overview of random forests and thinking about how might we apply it in forestry settings. And then the second part will actually step through an example where I do a tutorial with some tree biomass data. And so these are based on a couple of posts I wrote a few years ago that I think are going to be insightful for anyone wanting to learn random forests, seeing how they might apply it in forestry applications. And so random forests, like I said, are gaining in popularity. It's really been 20 years since they first came on the scene. And so 2001 and 2002 were the first papers on random forests that were written. And then really once the software, the package in R came out, lots more people started using random forests. So it's a quantitative method. It's a machine learning method. People like them, these random forest methods, because it can handle a large amount of data. One of the best things that it provides is the relative importance of a variety of variables. And it can be applied to classification or regression problems. That is, are you trying to predict whether or not something is happening, like a yes, no? Is the tree going to survive, in the future or not? Or it can predict regression. That is, what is the diameter of that tree going to be in 5 or 10 years? And so if you look at the literature, I pulled some data from 4 journals that are widely used in forestry and remote sensing. Those are the Canadian Journal of Forest Research, Forest Ecology and Management, Forests, and Remote Sensing of Environment. If you look at the trends in those papers and those journals, the number of papers using random forests has increased tremendously. It goes from about 40 papers in 2015 to almost 150 papers in 2019. And so just an incredible explosion of uses in the forestry discipline in the random forest method. And so in terms of how they work by taking first small samples of the data. And then any observations or anything that's not taken as a part of that sample is called an out-of-bag sample. And so those are used in the future in the random forest approach. What happens then is a series of regression trees are built. And then after that, the mean square error is calculated for each regression tree using those out-of-bag samples. And so after all those calculations are made, then the mean square error is averaged across all of the regression trees. And so that key value in terms of understanding how the random forests perform is that mean square error. What a lot of people like about random forests is the important scores for each of the variables that might go into your random forest. And so just like in a multiple linear regression framework, we might have 10 variables that we might think influences our response variable or our dependent variable. What random forest does and why people really like it is it provides an importance score for each variable. And so this is calculated by evaluating the regression with and without that variable. And so when you're evaluating that regression tree, the mean square error will go up or down or stay the same because each regression tree is different. So you can imagine those different variables contribute differently to each regression tree. If the percent increase in that mean square error after you remove that variable is large, well, then that would indicate it's an important variable. If the percent increase in the mean square error after you remove that variable is very small, well, it's not as an important variable because it's not changing the error in the random forest model. And so as an example, you might have a lot of remote sensing variables have a suite of different vegetation indices and other values that they might relate to something like tree biomass or carbon in a forest. And so you can rank all those different vegetation indices, put them in a random forest, and you'll get the most important variables and the least important variables. And so a percent increase in mean square error might be something like 60%. And so that would be a pretty important variable if it had an importance score of 60%. That would indicate the mean square error increases by 60% if you remove that variable. And so that's really one of the key things about random forests, is that they allow you to rank the importance of these different variables. And that differs from a regression standpoint, because in regression, you're often looking at something like p-values. And so you might say, well, I'm just going to retain all the p-values that end up being significant, say using a level of significance, the traditional use in statistics of 0.05. And so if that p-value is less than 0.05, well, I'll retain that model. And there are some regression techniques that you might be able to use to help you sort through that, like stepwise regression or backwards or forwards regression techniques. And so what people like about the random forest methods is that they can be used for a wide variety of variables. And what people will actually do when they have, say, 10 or 20 or even more variables is they'll actually prune the model to come up with a more parsimonious random forest model that has only a few variables. Say 5 variables might do all the prediction of something you're interested in, and you may not be concerned with the other variables that aren't adding much to the model. And so people really like random forests because they can handle all types of data. You can predict categorical data, continuous data, binary data. They often are pretty on par with other regression methods. That is, people will look at things like the percent of variability explained, which is analogous to an R-squared value in a more formal statistics framework. And people find that random forests provide just as good or sometimes better results than regression methods. And what people really like them, why they like them, especially in the remote sensing world, is that they work well with a large number of predictor variables. And so you don't have to worry necessarily about doing those stepwise regression techniques. Some of the limitations, they often are still considered a black box method. Now, there's a lot of work that goes on in the biometrics world and in the growth and yield world in forestry that people think are black box methods because sometimes models are complex. And especially so with the random forest methods. The models are not easily interpreted, so sometimes people can't always understand kind of as you change one thing, how does something else change? And so it's considered by some to be kind of a black box method. And then the other limitation is that they really require some model tuning for the best results. And so there are different parameters that you can change, things like the number of trees you try, things like how important do you want that variable to be. And so there's lots of different tuning techniques to really come up with a good random forest model. And so as an example, I'll step through kind of just a pretty basic example of trying to predict tree biomass using a random forest method. And so the data here are from 40 slash pine trees, and these are from Louisiana in the United States. And these were presented in a paper by Bernard Parasol in 2001. And so you can go to the paper and all of the data are right there. I mean, it's 40 trees. It's not a ton of data, but there are some great information on all of the tree dimensions and the biomass components for all of those trees. And so I'll share the link to this in the notes, but you'll see that there's a link to the data where you can kind of follow along and see my approach as I've done this and implemented it in R. But generally, the ultimate interest in this tutorial, in this method, is to predict tree biomass in all of the components. And so that would include the green mass of the wood, the bark, and the crown, using all the common tree measurements that we have. So we have tree diameter, height, live crown length, and age. And so just kind of a quick summarization and kind of a exploratory data analysis of these data. It looks like the correlation between DBH and the biomass of the tree is 0.92. So that would indicate, we could potentially use diameter as a predictor of biomass. The correlation between height and biomass is 0.85. And you can begin to see that, some of these common forest inventory measurements are going to lead us to understand what the biomass of that tree is. And so what I've used here is an R package, random forest. Now, there are lots of packages in R and in Python that implement machine learning methods like random forests. This package that I've chose to use is the random forest package, which was developed in the early 2000s as a part of some of that early work on random forests. And so the code is really pretty simple. Any of you that have fit regression models or other modeling techniques in R will kind of get the sense of the structure of how you specify the model. And so the random forest function is a part of the random forest package that allows you to do it. And so we were going to predict the biomass of the tree using the diameter breast height, the height, the live crown length, and the age of that tree. And so one of the things that we can look at, after we run the model, is to look at how important those variables turn out to be. Now here we get a ranking of the importance scores for all of those variables. And I like the random forest package because it provides a simple graph that you can output that visualizes those importance scores. And so what we see here is that both DBH and height are the top two ranked variables. And so they have importance scores, or their values for the percent increase in mean square error if you remove those variables are around 16%. And so the third ranked one is live crown length, which is around 14%. And then the last ranked variable is age of the tree, and that ranks at about 8%. And so you can see that, if we're only going to choose one variable to use, we might want to choose DBH or height and maybe not age, because it seems like if we were to remove age, it wouldn't have as much of an impact on the tree biomass as those other more common forest inventory variables would. And so one of the other things that when you fit a model like this is you get a value, might call it an R squared. That's how we would call it in a more traditional statistical framework. But you get a percent variance explained. And so with the random forest model, we get a percent variance explained of 88.6% using the random forest method. Now, what a lot of people like to do is to compare that to a more traditional linear model. And so we can do that as well. So a linear model fit with the same data, the same model, we get an R squared value of 0.91. And so you can see there that, well, in that case, it looks like the linear regression model actually does a little bit better, at least in terms of explaining the variance, than the random forest method does. It's about a difference of 3 percentage points. And you get, obviously with the regression model, you get the parameters and you get the standard errors of those parameters. And so you can make new predictions with the model that you've developed. You can also compare things like the standard error, the mean square error, and some of those different things. What I like also, if you're working in the R environment, is that you can use functions to predict what the values might be, and you can kind of compare the predictions and the residuals from different predictions using a random forest approach and also a regression approach. And so that's of interest in a lot of ways. And so again, you can kind of compare those different methods and see which method you might prefer for your own data set. And so again, to kind of summarize, these random forest methods are really flexible and they can be pretty comparable to other regression or classification methods. People like them. They can handle all types of data, whether it be binary, categorical, or continuous. And they work well with data sets that have a lot of variables. And they help you to kind of sift through all those variables to see which ones might matter in terms of your own analysis. There are lots of ways to do this. R has a lot of packages. Python has a lot of packages. Lots of support online for learning random forests and implementing them. And like I said, I'll add two blog posts that I wrote a few years ago into the notes that kind of step through these examples, and you'll be able to see that tree biomass data that I was talking about, and you can kind of work through on your own. So thanks, everyone. We'll check in soon. Thanks for listening to the Forest Analytics Landing Podcast. For more information on how data and analytics can empower your organization, visit arbor-analytics.com.